Alright, we're going to go ahead and get started. Were there any questions from last time on our calculus homework? Okay. So last time we talked about section 7.5. We didn't quite finish. We talked about spring problems, and we talked about the problem of lifting a chain or something attached to a chain, lifting a weight basically, and finding how much work was done in both of those instances. The third type of problem we have is emptying a tank of liquid. Okay, now when we look at this problem, there's specific elements that we need to include. So the work done is equals an integral, of course. Now the three elements that we have are the weight, and this would be the liquid weight per cubic foot times the cross-sectional area of the tank times, and we need the last thing we need is the vertical distance to the pump. In this case, the liquid exists between heights C and D. Basically, that's where the liquid is. So if typically we'll go from 0 as our C value, our lower limit, and then to whatever depth of water that we have for D. So if there's 10 feet in the tank, we go from 0 to 10, generally speaking. Now, when we talk about emptying a tank of liquid, there's a couple of different ways that we could do that. And what we're looking at here is we're considering pumping up the liquid from the container. So our pump is located above where the liquid is stored. So because it has to travel upward, there is an amount of work that is required to achieve that. If we were to open a drain at the bottom, in that case, then we wouldn't need a pump to be doing any work because gravity would be doing all the work for us. Although if we did open a drain, then that would actually, if we wanted to figure out how long it would take for the tank to be emptied, that's more of a differential equations question, because it does require a little bit different approach. But we'll talk about that in that course. So for now, looking at emptying a tank of liquid, We're assuming the pump is located above the tank, and we're going from there. Okay. So this is kind of our general approach. So let me present you an example. Let's say we have a swimming pool. With 5 feet of water. Has a rectangular shape. That is, let's say, 30 feet long and 20 feet wide. The pump is located at the top of the pool, 6 feet from the bottom. Okay. And so finally the question is, how much work is done in emptying this pool of water? Okay. First thing we need is liquid weight per cubic foot. Now for water, that is 62.4 pounds per cubic foot. Now, if we're given the weight, if it's in metric, then we have to make sure we include gravity with that, because it's always mass times gravity. But when we talk about weight in pounds, then gravity is already included. Anyway, the cross-sectional area, the idea here is that if we take a horizontal slice of this 3D object, what is the formula for that area? Now, if we have a cylindrical or rectangular tank, such as we have here, then the cross-section is just a constant value. In the case of a rectangle, it's length times width. In the case of a cylinder, it's pi r squared. Okay. And maybe that we have a conical tank sitting on its end, in which case we get a circular cross section, but at different heights it'll have a different radius, and we would have to adjust for that. I'm just going to do a relatively simple problem here, where we just have a constant cross-sectional area. The other thing that has to be considered is the vertical distance to the pump. Now, our swimming pool has 5 foot of water, so that means for our limits we're going to integrate from 0 to 5. However, because the pump is located 6 feet from the bottom, basically there's a foot between where the water stops and where the pump is located. So 5 feet of water, 1 foot of space, and then our pump is at the top edge of the pool. In this case, we're going to have to account for that distance. Let me go to the next page. I'll show you. Okay, so if we use water, we know 62.4 pounds per cubic foot is our force from water. And we know our area is just length times width, which in this case is 30 times 20. So we have 600 square feet. is our cross-sectional area. And then our, if we think about, okay, our pool, here we have 6 feet, and inside the pool we have 5 feet of water from here to here. Okay, 6 feet is from there to there. And then we have, this is our pump. Okay. And so the idea is at depth y, how high would the water have to travel to reach the pump? Well, we know if our total distance is 6 feet, okay, from the pump to the base of the pool, then when the water is at depth y, then the distance here is whatever that total distance is minus whatever y is. So the distance from the water surface to the pump is 6 minus y, where y is the current depth of the water. Hopefully that makes sense. So, to set up our work problem, you know, we integrate 0 to 5, then we have 62.4, then we have 600, and we have 6 minus y, and then dy. Okay. And so, if we look at the units, we have pounds per cubic foot, and we have square feet, and we have feet. And these are all being multiplied together. Now, square feet times feet is cubic feet divided by cubic feet. That cancels. So this still represents pounds, and it's being integrated over a distance, so our work will be pounds and feet, pounds and distance. Which is how we expect work to be measured in the first place, is foot-pounds, or so whatever combination of units we're working with. A weight measure and a distance measure, or it could be Newton meters if we're using a metric. So, all right. So this is our integral. Now, 600 times 62.4, we can go ahead and multiply that and factor it out. That's 37,440. And we still have integral 6 minus y minus, or times dy. So from there we can just complete our integration, which is 6y minus y squared over 2. And that's from 0 to 5. Now we know the 0 is going to give us 0 and 0, so we don't really have to worry about plugging that one in this time. So we'll just plug in our 5. 6 times 5 is 30. 5 squared is 25, divided by 2 is 12.5. So our work ends up being 37,440 times, this will be 17.5. Times 17.5. So our work is 655,200 foot-pounds. Okay. Hopefully that makes sense, the approach that we took there. Again, it's set up in a specific way, so it's possible that our cross-section, whatever horizontal slice we take of this tank, it's possible it has a variable in it, and that's where we have to be careful, is if the tank is not a consistent shape, like it's cylindrical, well, not cylindrical, if it's conical, or if it's like a spherical, which is something we do see, at least maybe hemispherical. Yeah, so we do have to pay attention to the shape. Excuse me. Alright, so in this case, because we had a constant shape, because we had a constant cross-section, that made it a lot easier, but the only thing that may change is this expression here may have a variable in it, and we'd just have to multiply all that together and then integrate. So, as far as the medium goes, water is 62.4 pounds per cubic foot. Oil is 50, I know. Those are the only two that I know off the top of my head. But we have to know exactly how much that fluid weighs, whatever fluid is that we're working with, because that does affect the actual weight of the water that we're trying to pull out, and as a result affects the amount of work that needs to be done to pull it out of there. So, okay. So that's the last problem I wanted to do for section 7.5. So let's continue to section 7.6. And here we'll talk about centers of mass. Which we'll also see called centroids. Now, before we look at how we would apply calculus to this, let's look at some of the simpler versions of this that if you've taken like a high school physics class, then you've probably already seen. Or even if you're in physics now, probably are familiar with this. So centers of mass problem are fairly common, but when we're starting out in like a general physics class, we don't really look at things from a calculus perspective. We look at things from a it's really just algebra perspective that we have to use. So we're going to look at the one-dimensional case. And as an example, I would like to have, let's say that we have three different masses at three different locations. So we have three masses, which we're going to identify the masses as M1, M2, and M3. at 3 different locations. And the locations we're going to identify as x1, x2, and x3. Okay? Now the idea is, okay, one-dimensional case means that this is a line that we have. We'll call the center right there 0. So maybe we have one mass located here. Here's x1 with mass m1. The second mass is located here at x2. And the third mass is located here at x3. Okay. Now, if we want to calculate the moment, in this case, the origin is kind of like the fulcrum of a fulcrum. Is that the right word? Of a seesaw. You know, if we're trying to balance this on a single point located at the origin, essentially. Maybe we have a situation such as this. The moment is basically the tendency of this one-dimensional line or object to rotate around this origin point. Okay. Now, if the moment is 0, that means there's 0 rotation. It's going to be perfectly balanced. But if the moment ends up being negative, then it's going to tilt to one side, and if the moment's positive, it's going to tilt to the other side. And that's what we understand in the one-dimensional case. You know, either it balances or it tilts to one side or the other. And so our moment, which we'll identify as m, is going to be m1 times x1 plus m2 times x2 plus m3 times x3. So basically each of the masses is located by how far it is from the, it's multiplied by how far it is from that origin spot, from that balancing spot, potentially. And if we end up with, you know, x1 and x2 are probably negative values since they're to the left of the origin. x3 would be a positive value since it's to the right. So if we end up with a negative moment, then it's going to want to tilt to the left around that balancing point. And if we end up with a positive, it'll want to tilt to the right. Okay. And if our moment is 0, then it'll be perfectly balanced. That's how we would determine that. So the concept is that we have these different point masses on this one-dimensional line, and then we see, you know, where the moment is as far as whether it balances or not. Most of you, I mean, probably already knew that stuff. Even the two-dimensional case is not terribly complicated. Now, when we say two-dimensional, we're going to look at the what we call the discrete case first. Okay. Once again, we have 3 different masses, m1, m2, and m3. But mass 1, for instance, is located at x1, y1. Mass 2 is located at x2, y2. And mass 3 is located at x3, y3. So because we're looking at a two-dimensional case, each of our masses has an ordered pair that represents its location. x1, y1 for mass 1, x2, y2 for mass 2, and x3, y3 for mass 3. Now, when we talk about the moment, in this case, we think of the balancing point as the origin still, which is right in the middle, and maybe a good example for this is kind of, instead of looking at a seesaw like we did in one dimension, an example for this is like the waiter's tray in a restaurant, where you hold the tray so that the objects on the tray are balanced. That is the balancing point, okay? And so wherever the center of where the waiter is holding the tray is, then that will be the balancing point. And so we'll have zero momentum in any direction from there. But when we look at the moments or momentum here, we look at this in terms of the x and the y-axis, because that's what we have available to work with. So we can have mx, which is defined as the moment about the x-axis. And then we can have my, which is defined as the moment about the y-axis. Okay. Now, when we talk about the moment about the x-axis, that's the tendency, if we look at the horizontal x-axis, that's the tendency for this plane to rotate around that x-axis. Okay, so it's, is it tilting forward or backwards, basically. Now, what's going to make it tilt to one side or the other around that x-axis is going to be the vertical distance to each of these masses. Okay, so we have a vertical distance here, a vertical distance here, and a vertical distance here. And when you talk about the vertical distance, we're actually talking about the y values. Okay, so even though we're talking about the moment about the x-axis, that means the distance from the x-axis vertically depends on the y values at each of these mass locations. So mass 1 is affected by its vertical component y1. Mass 2 is affected by its vertical component y2. And mass 3 is affected by its vertical component y3. So we multiply those together. So basically this is it's almost like it is a weighted average, basically, where the quote-unquote weight is actually how much mass is at that location. It's not truly a weight because we know it's a mass, but when we say weighted average, we don't literally mean weight. So M1 is located y1 units from the x-axis, so that's how much that mass is counting, basically, when we multiply those together. And the same for the other two, and we add these products together to get the moment about the x-axis. Now our y-axis, that's our vertical axis. Okay, think of it as a flat plane now, a vertical axis. That's the tendency to rotate left to right around that vertical axis. Now, with the plane tilting to the left or to the right, that's going to depend on how far the objects are in those directions, left or right, of the central axis. So to get to each mass, we have to look at the horizontal distance to each mass from the axis. So mass 1, this is x1 units from the axis. Mass 2, y2 or x2 units from the axis. And mass 3, x3 units from the axis. So long story short, if we're finding the moment about the x-axis, we use the vertical components, or the y values, basically. And if we want the moment about the y-axis, then we use the horizontal components or the x values. Okay? It's kind of backwards how we might initially look at that. But once we think about it, I think it makes sense. Okay. The third thing that we would like to calculate is m. This is the total mass. Because certainly this factors into the calculation. So the goal here is still to find the center of mass for these three different point masses that we have. And it's completely based on their location and the size of the mass. And so we've calculated mx, we've calculated my, and we've calculated little m. And so finally, our center of mass x bar, we'll say, is my divided by m. Y bar is mx divided by m, and x bar comma y bar is the center of mass. That's the coordinate location of the center of mass. So in each case we have to divide by the mass in order to properly account for those objects. Okay. And again, x bar is associated with my because that's where all of our x values are represented. So that's going to tell us ultimately the center in the x direction and the center in the y direction, and so we're together that gives us the center of mass overall. Okay. Now that's a discrete case. Again, we still haven't done any calculus in these calculations. All of that is basically just multiplying, adding, and dividing numbers, which that's arithmetic. But now we look at the third case that we'll examine, which we'll call the continuous case. So this is the two-dimensional continuous case. And the idea is that now we have a shaded region bounded by a and b on the left and right, and two different functions on the top and bottom, and we want to find the center of mass of this shaded region. Now, one thing I want to stress is that we're assuming that this mass has constant density. In this case, if we're thinking about the object as a flat plane, the density is actually basically the thickness of this plane, and that's how we would display it from a visual standpoint. So if we had a really dense object, then that would certainly give, if it's denser in some parts than another, then we would acknowledge that by showing a greater thickness in that area. And the way that we do that is it actually require a graph in 3 dimensions, like a 3-dimensional volume graph, where the thickness changes from one part to another to kind of illustrate what the density is at those different locations. We're going to assume that the density is constant and the same throughout because we do not yet have the means to work a 3-dimensional problem. That's something that you'll do in Calculus 3. So you have that to look forward to, I guess. But it actually doesn't add a whole lot of difficulty beyond what's already here. So by the time you get to that point in Calculus 3, you'll probably be all right with that. So it really is part of the gradual approach to learning math. Anyway, so we're going to assume a constant density. And so we're going to leave density out of our calculations because of that. Now, the reason that we can leave density out of our calculations is that we would have to include density as part of our moment about the x-axis, the moment about the y-axis, and as part of the total mass, because the density would affect the mass as well. But because density would be part of all 3 of these things, when we go to divide my divided by m, since density is part of both of those, density effectively cancels out if it's identical, if it's constant. Same thing is true here for the y bar, because mx and m both include density as a product in that calculation. They would cancel each other out, and we wouldn't have to worry about it in that scenario. That's why we can safely say we can assume a constant density and then basically ignore it. Okay. Remember that density equals mass divided by volume. So if we turn that around, we can say mass is equal to density times volume. And by assuming a constant density, then because density is connected to all of the masses individually, when we divide those out, it goes away for all intents and purposes. So, all right. So the goal is to find the center of mass. Now, just like in our discrete 2-dimensional case, we have to find mx and my, the moments about the axes. Now, the moment about the x-axis, mx, again, that's going to be the vertical component here. So the vertical component of for this shaded region, when we look at that, basically that means we're going to find the midpoint or the midway point between f and g, between the top and the bottom edge. Now the midway point would be the sum of the 2 functions divided by 2, basically, and that would give us a curve that models the halfway point. Okay, so we take the halfway point from each, between the top and the bottom, and that kind of gives us a reference point for that particular x value. So that's F plus G divided by 2. And then we look at how much of that mass is associated with each of those points. So if we pick a point right here, this point's halfway between F and G, so that's its location. And then we look at the vertical distance here, which is F minus G, and that's how much is so that's essentially our mass at that location. So we have our location, and then we have our mass. And we want to do that for each x value between A and B. And so our calculation for mx is F plus G divided by 2 times F minus G dx integrated from A to B. Now, another way that we could express that because we have F plus G times F minus G, we could actually multiply those together and say it's F squared minus G squared. That's a difference of squares. If we were to multiply them, we still have the 1/2, of course. I find overall that this formula may be a little bit easier to use than the other. Or it just may be that it doesn't really matter. Both of them are equally bad. One of the issues we'll find in these problems is that they do take quite a while. And you'll notice I posted an announcement earlier today talking about the upcoming test on Chapter 7, which will be next week. So on Tuesday we'll review, and then after Tuesday you'll have the window of time during which you need to take the test. Most of the test, about 2/3, is in class, and that covers sections 7.1 through 7.4. And then the material from 7.5 and 7.6 will be on the take-home portion, and that'll just be due by the following Tuesday. Okay. 7.6 in particular, because this is just mx. My and m are two more integrals that we have to find, and they're not particularly easy either. And then we have to find our center of mass based on that, or centroid. That's why I want to make sure that you have this one as a take-home problem. It just takes so much time to go through this, and I don't want you to rush and get things wrong. So the main thing is that we're able to work through and get the correct answer, because this one will take you a long time. Even though the work is probably pretty easy, it does take a while to get there. Okay, let's continue with my. Again, integrate from A to B. Now for my, this is the tendency to rotate around the y-axis. So we may choose some point x. Well, no, I did that wrong. It's the vertical component, not the horizontal component. Sorry. And the reason we do look at that is we pick an x value, and this is how much mass is associated with that x value, and we want to look at its tendency to rotate around the y-axis. And so we look at the horizontal component to that point, which is just the x value, times how much mass is at that location, which is the vertical distance from F to G. So f of x minus g of x. And we'll just integrate from A to B. The my is a little bit easier than mx in that regard because of that. Lastly, we have m, which the mass of this object. Remember, we said mass is density times volume. Now, we're assuming a constant density, so we can ignore it. So we really were thinking about volume. Now, for volume, really we're just looking at area, but with a thickness of 1, because we said it was a constant density. So if we said that the density is 1 everywhere, then really we just want the area of this object, which is the integral from a to b of the top function minus the bottom function, going back to 7.1. So it's just a to b f of x minus g of x dx. So those are our formulas for mx, my, and m. And once again, x bar equals my divided by m, y bar equals mx divided by m, and then the center of mass is x bar comma y bar. This doesn't change from the last example. Okay. So once we get those 3 values, or 3 integrals completed, then we can put them together like this to calculate where the center of mass is located. Okay. Alright, so now that we have the formulas down, let's actually apply it to a problem. Let me see if I find one that I like. So let's find the center of mass of this region described here. Y equals 4 minus x squared, x equals 0, and y equals 0. Now, if we want to go ahead and sketch that. 4 minus x squared, I should probably include x equals 2 here. 4 minus x squared is a parabola that starts as 4 and goes down from there. Okay. This is 2, this is 0, and this is 0. And so we end up with this as the region that we want to find the center of mass for. Okay. Scale's not exactly equal here, but we kind of get an idea of what we're looking at. Probably the center of mass will be somewhere in here. So maybe a little bit left of 1 and a little bit below 2 vertically. But we'll be able to calculate it exactly. I'm just kind of eyeballing where it might be. Alright, so we talked about our top function being f of x, our bottom function being g of x. F of x in this case is 4 minus x squared, and g of x, our bottom function, is just 0. A is 0, b is 2. Those are our limits of integration. Okay. And so that's going to help us set up each of these integrals now. Now, for the mass, we said, okay, we just find integral 0 to 2 of f of x minus g of x, so that's pretty easy to set up. There's our first integral. And so that will be 4x minus x cubed over 3 if we integrate. And if we plug in our 2, we get 8 minus 8 over 3. If we plug in 0, we get a pair of zeros, so there's nothing lost there. And so our mass is, let's see, that'll be 3 times 8 is 24, minus 8 is 16 over 3. Technically, the mass is 16/3 times the density, but again, we're just going to leave density out of this. Now, mx is probably the most complicated of the calculations. We said it would be 1/2 integral a to b 0 to 2, and we would take f of x squared minus g of x squared. The good news here, at least, is that g of x is 0 because it goes right to our axis. So it does save us a little bit of time and effort doing our integration. So we continue with what we have, simplifying. So if we actually just square 4 minus x squared, that's 16 minus, let's see, that'll be 8x squared, and then plus x to the 4th dx. So that's 16x minus 8/3 x cubed plus 1/5 x to the 5th from 0 to 2. And so that's going to give us, if we plug in x equals 2, 16 times 2 is 32. 2 cubed is 8, times 8 is 64 over 3. And then 2 to the 5th is 32 over 5. And for this, I'm just going to go ahead and throw it into the calculator. So we take 32 minus 64 over 3 plus 32 over 5, and then we divide that by 2 because we have a 1/2 on the outside. So it's 8 and 8/15, or 128 over 15. Okay, so that is mx. Lastly, we want to calculate my, which I may not have enough room here. My is integral 0 to 2, and we have x times f of x minus g of x. Okay. Well, that's just x times 4 minus x squared, so we have integral of 4x minus x cubed from 0 to 2 dx. Integral of 4x would be 2x squared. Integral of x cubed would be 1/4 x to the 4th. These are from 0 to 2. So, let's see, we plug in the 2, so that's going to give us 2 squared is 4, times 2 is 8. 2 to the 4th is 16, divided by 4 is 4. So, my is simply 4. Alright, so we calculated m, we calculated mx, we calculated my. Last thing we need to do is put those together to find our center of mass, or centroid, as it is also called. Alright, so x bar we said was my divided by m, so we'll take 4 divided by 16/3. Four divided by 16/3 comes out to be 3/4. So we'll call it 0.75. Y bar we said is mx over m. Mx is 128 over 15 divided by m, which is 16 over 3. And that comes out to be 1 3/5, or 1.6. And so our center of mass is located at 0.75, comma 1.6. Which sort of agrees what we said before, where we knew it would be a little bit left of 1 and a little bit below 2, because it's not, it's not a perfect rectangle, so it's going to be shifted over from that. But yeah, we end up with 0.75, comma 1.6. All right. So as you can see, the biggest concern in a problem such as this is the 3 different integrations that we need to complete in order to successfully arrive at the conclusion. And that's really why I would like to include this on a take-home problem rather than one that you have a time limit for. Because I want, especially, and this one I did was fairly easy because g of x was 0. The one I have for you in the test is not the case, that g of x is 0. So that means you're going to have a little bit more work to do in each of these integrals than what we did even on this example. So make sure you follow those formulas that I gave you. And as long as you go through and do all of our calculations correctly and all the integrations correctly, it should work out. But like I said, it does require time. So in that way, this is probably the most involved problem. Even though the integrations we did were not difficult at all, there's so much detail work there, it makes it a little bit more time intensive than anything else. So that's the real concern here, is the amount of time it takes to work this kind of problem, even though the actual individual pieces are pretty straightforward. Okay? So that wraps up everything I wanted to do in chapter 7.6, or chapter 7 for that matter. So I think for today, unless there's any questions, we'll go ahead and stop there. Does anyone have any questions? So in Tuesday's class, we will review, and largely that will consist of me working through any questions y'all have in review problems, or if there aren't any specific questions, I'll just go through different review problems. And we'll also talk about in a little bit more detail, like how many problems are on the test versus what's in class that you have to complete in the time period provided for the exam versus what you'll have to take home. So I can tell you it's probably going to be like 6 or 7 problems in class versus 3 take home. So something in that regard. But all right. So I think we'll go ahead and stop there for today. If you do run into anything on the weekend, be sure to send along any questions. If you want to practice one of these for homework, I would suggest on page 502, go ahead and look at number 21 for homework. That would give you a chance to practice one of these problems at least, and kind of get a feel for how it's going to work. The one I give you on the test won't be any more difficult than that one is. So, if you look at this, it gives you a combination of different functions. The other issue with 21 here is that we actually have to set the equations equal to each other so that we can find the limits of integration as well. And that'll be another challenge there. So, all right. Well, I hope you all have a good rest of the day, good weekend, and make sure you look at my announcement in Canvas if you haven't already to get the review problems and some of the details about the test that's coming up next week. But like I said, Tuesday we'll have time to go over any questions we have on review problems, so I want you to work on those as well. But otherwise, take care, and I'll talk to you all then. Bye.